anyway. Okay, so from our work we've done with the definite integral, we have arrived at some things that just make sense because of how math works. And I don't really like calling them rules, they're just more properties because, in my mind, because they just arise of, you know what, that's the way math should work. If this is all of the math we've been doing so far, this new math, this calculus should fit into that. So for example, if we have in number one, the definite integral from a to a of f of x dx, if we think about it, we've got a shape that has a side of length 0. What's going to be the area of a rectangle if one of those side lengths is 0? There's no area there. There's no shape formed. Some of these other ones are less clear. Like I think the second one and the third one are less clear. But if we look at the notation, we can observe very subtly that the notation is different. We're used to going from A to B, and this is why it's so important to read your notation correctly. This is from B to A. So what does it mean if you're going from B to A? It means you're going backwards. Normally, I think you would agree, we read a graph from left to right. We've been doing our areas from left to right. So what does it mean if you switch those? If you go from 4 to 3, for example, instead of 3 to 4, what's happening is you're saying, I'm starting here at 4, and then I'm going to the left to get to 3. So what effect does that have on the value of the area? The value of the area becomes an opposite. And I don't say negative, I say opposite for a very precise reason that may become or may make sense to you if we look at the graph, which we will in just a little bit. For the third one, this third one I think is also less clear. So if you're multiplying a function by a constant, you can multiply the area by that constant instead. And the reason why I think it could make a little bit of sense is if you think about how when we were starting out, we had base times height, base times height, base times height, right? So if we did 3 rectangles, it might look like that. You can factor out the base if it's the same. So that's kind of the thinking here, why I think this property flows naturally from what we've studied. The next thing I think really makes a lot of sense based on what we've studied, and it says specifically, if I'm going from A to B of 2 different things, I can find their areas separate and add them together. That makes a lot of sense because of what we've been doing with shapes. Just like in the fifth property. In the fifth property, we have an integral that starts at A, goes to B, and then we have a second integral that starts at B and goes to C. And what we're doing is we're saying that if I add these 2 integrals together, that's the same thing as if I just go from A all the way to C. I think that makes perfect sense, doesn't it? One is saying do it in sections. The other one is saying do the whole thing. They're equal. I think that 5 is a version of 4. The other thing I'll mention, and I just want to make sure it's clear to you, is that these are all bidirectional. What do I mean by that? I mean, you can also go read your equal sign from right to left. So 0 could start and then say 0 equals the definite integral from a to a of f of x dx. For the second one, you could say the opposite of the definite integral from a to b of f of x dx equals the integral from b to a of f of x dx. You could say k times the definite integral from a to b of f of x dx equals the definite integral from a to b of k times f of x dx. So I'm not going to read all of those or go through all of those. Just try to make that point. So there's a lot of really nice practice on here if you're looking for more practice to do while you're studying. I just want to look at a few of the properties to help you understand how we might do some of these. So the first one I want to look at here is E and F. So E and F are the same but for the direction. So what do I mean by that? E is the definite integral from 3 to 6 of f of t dt. So that is along the x-axis or t-axis, however you want to think about it, from 3 to 6. And then we use that. So that's a triangle, right? Yeah, that's a triangle, okay? So if I go from 3 to 6, I know that I'm finding the area of a triangle, so 1/2 base times height. So if I go 1/2, the base is from 3 to 6 is 3. The height, though, is different. Remember, the heights, if you will, are function values, and every one of these function values is negative. So that height or function value is -1. So E is -3/2, right? It's a triangle. It's a triangle that goes below the x-axis. F is not -3/2. F is +3/2. So why is F +3/2? That's because this definite integral from 6 to 3 is equal to the definite integral from 3 to 6 if we take the opposite of it. So in the first case, again, we're going from left to right, the normal direction. In the second case, we're going from right to left, the opposite direction. Since we're going the opposite direction, we have the opposite of this area. All right. So we're not going to calculate it, but I would just want to look briefly with you at J. So J is the definite integral from 0 to 10 of f of t dt. So what is that? That is this area. So start at 0, go to 10, along the x-axis, the horizontal axis, and then follow the function. How would you find that area? How'd you do it? Well, I bet you would say that you'd find, and forgive the notation, the integral from 0 to 3, add that to the integral from 3 to 6, and add those two to the integral from 6 to 10. Right, that's what you do. You do these 3 separate calculations, add them together, and that will give you the whole calculation, wouldn't it? Yes, yes it would. All right, so there's really interesting practice on here with the absolute values. We're not going to look at those, but we are going to draw our attention to the next page. So the next page is, believe it or not, the exact same thing as the first page. But what's different here is instead of you being forced to calculate the area from -2 to 5 of some function f to get 18, and calculate the area from -2 to 5 of g of some function to get 5, and then do the same thing from -2 to 5 for a third function h, get an area value of -11, and then going back to f, going from -2 to 8 and determining that that area is 8. Those values have already been provided. So what we're going to do a little bit of here is just check out how does this work if we think about those properties. So you don't have to do letter A this way. Letter A, by the way, is read as the definite integral from -2 to 5 of the sum of f of x plus g of x dx. But the way I was thinking about doing it is based on those properties that we've been studying, specifically the definite integral from -2 to 5 of f of x dx. I'm going to do that one, and then add that to the definite integral from -2 to 5 of g of x dx. Makes a lot of sense, right? That's the way math ought to work here. Well, integrals are no different. They work the way they ought to. So the area, I don't have to calculate it, it's given to me. For f is 18, and for g is 5, which means that we have a value here of 23. Pretty nifty. Let's draw our attention over here to letter C. So letter C is the definite integral from 5 to -2 of 4 g of x dx. And I'm going to pause the recording here and give you a little bit of time here to do some practice and or ask me questions. I hope you gave that one a good try. There's a couple of interesting tidbits here in letter C. So one of those tidbits is, I don't know if you noticed, but 5 is, sorry, not less than. 5 is greater than -2, isn't it? Yes. So this is going from right to left. So that means we should think about how this is going to be the opposite if we go from -2 to 5. The next thing that's interesting, I think, or why I had you do this problem, is this 4 here. That is a constant multiple. So what I can do is slurp that 4 out, factor it out, if you will, and think about how I have the opposite of 4 times, forgot to write the time symbol in, sorry, the definite integral from -2 to 5 of g of x dx. And that then is a question I can answer. I can definitely do -4 times 5 to get a value of -20. Pretty nifty. Yes, no? Perfection. Okay, we are going to look at a couple more of these, but not today. They are going to be part of your practice that will come on Thursday and Friday. So there are excellent problems on here you will be seeing again, but because of how the week is structured, I decided to defer practice from today that you might do independently for home fun to later this week. And we are going to shift gears here and talk about a new thing. But first, I want you to go to your happy place for 30 seconds. Okay, here we go. So we've been looking at the exact area between a function and an axis. And we looked at 3 versions. Well, this is the 3rd version. So this 3rd version is going to introduce a new idea. Okay, this new idea, this new operation is called anti-differentiation. And anti-differentiation is exactly what it sounds like. We've talked about this briefly before, but it's been a while. Anti-differentiation is appropriately named. It means literally reverse to get the derivative, or find the function whose derivative is given to you. That's what it means to do an antiderivative. So you're reversing the process of differentiation with all those shortcuts and things we did. Sorry, I'm having technical Zoom issues here. Okay, should be good here to finish up just in time. All right, so that's what anti-differentiation means. Reverse the process of differentiation, or whatever function you have, find the function whose derivative is presented. Now we're going to start off with a little bit more vocabulary and a touch of notation. So the function whose derivative is the integrand. What do I mean by integrand? What I mean by integrand is inside sorry, I don't want to write definite. Inside the integral notation. But we'll come to that. First, what I want you to do is while you're looking at this, I want you thinking about, while you're writing this down, I want you thinking about, okay, what function has a derivative that is 2x minus 2? That's what I want you thinking about. And I just want you to write your guess on your paper. Okay, so that's all I'm asking you to do. While you're writing all that down, think about what function has a derivative that is going to be 2x minus 2. Okay, so that's what I want you thinking about while you're getting that all copied down. And then we're going to check to see if any of you got the one I came up with. And by the one, I actually mean the 7. Yes, 7. And that's not even all of them. Okay, so let's see. I need a function whose derivative is 2x minus 2. So did you think about if you take the derivative of x squared, you get 2x? Yeah, thought about that. Did you think about how if you took the derivative of negative 2x, you get negative 2? Yes, okay. That's not the one I came up with. That's one of them. Actually, I only came up with 6. Sorry to lie to you. These are the 6 I came up with. So I came up with x squared minus 2x. I also came up with x squared minus 2x plus 11. I also came up with x squared minus 2x plus e. Also came up with x squared minus 2x plus the natural log of 5. Also came up with x squared minus 2x plus the sine of 2. And also came up with x squared minus 2x plus the arctangent of the cosine of e to the power of 6. Yeah, I came up with 6. And honestly, that's barely scratching the surface of the correct answers here. There are infinitely many correct answers to this question. So I was obviously playing math games, right? I was having a lot of fun here when I came up with 6. 6 is not infinity, but 6 is, I think, enough to prove the point. And the point is this, and I'm only looking at one of these to illustrate my point. If you add 0 to 2x minus 2, don't you get 2x minus 2? Yes? 2x minus 2 plus 0 is 2x minus 2 for sure. And check this out. What's the derivative of 11? Derivative of 11 is 0. What's the derivative of e? The derivative of e is 0. How about the derivative of the natural log of 5? The derivative of the natural log of 5 is again 0. Derivative of the sine of 2, also a constant, 0. Derivative of the arctangent of the cosine of e to the power of 6, once again, a constant, therefore 0. So how do we negotiate this given that there are infinitely many correct answers? What do? Well, we get fancy with the math. And we say an antiderivative, and I'm down here in red, of 2x minus 2 equals x squared minus 2x plus capital C. C is understood to be any constant. Now, there will be situations where we are able to determine the exact constant, but for right now, starting out, we are not there yet. We only know that there is a constant because the constant, or I'm sorry, not that there is, that there could be a well, let me rephrase. That was poorly done. There's always a constant. Sometimes the constant is already 0, right? That's possible. 0 is a constant. So are any of these other options I've presented or anything else you could imagine. So we use capital C to say any constant. So Notation. We have the integral symbol dx with 2x minus 2 inside. We'd say this is equal to x squared minus 2x plus c. C is any constant. Okay, think of it as a placeholder. It's our observation to somebody looking at our work to say, there is a constant here. I don't have enough information to determine it. Okay, that's what the C is. Now, we talked about this briefly again. Let me reiterate it. This is an indefinite integral because there are no defined limits of integration. So if you think about every single one of the integrals we've evaluated, they've said start at this x value, end at this x value. This is an indefinite integral, or I usually think of it as just performing the antiderivative operation. So what we're saying here is we're not specifying from this x value to this x value. Furthermore, we're not specifying what the constant is. There has to be one, even if it's just 0. We're just saying, tell me the function whose derivative is the integrand. And integrand, again, and please make sure you have this written down in this context, that is the function that is inside of the notation that indicates integration. So that is the integrand. So what we want to do, what this notation tells us, is find a function whose derivative is 2x minus 2. And we do that by looking at x squared minus 2x plus c. The derivative of x squared is 2x, the derivative of negative 2x is negative 2, and then the derivative of any constant, no matter what its value is 0. The derivative of c is 0. Okay, we're going to look at one more thing here today. And I just want you to try it out. Nobody saw that, right? Nobody saw that. We're going to look at this function. It is find an antiderivative, or this is an indefinite integral of the cubed root of v dv. So we have a function. The function's variables are v. We have the cubed root of v. And we want to come up with the function whose derivative is the cubed root of v. That's what we're trying to do. So we're going to be working on that. Now, for video purposes only, I'm going to show what the correct answer is, but don't look at the screen for a little bit here. I just want to stop the recording. So no peeking at my screen.